In this video, I'm going to talk about the enhanced greenhouse effect. Not just what the greenhouse effect is, but rather how humans are also increasing its effect on the Earth. Please read the success criteria I plan to cover during this video. So what I have here is a simplified model of what's going on with the Earth and radiation from the Sun. So I have here that it's 343 watts per meter squared. That's the intensity that's actually reaching us from the Sun. I have an albedo of the atmosphere, which is approximately 0.3. That will be affected by the amounts of clouds or dust in the air, or things like that. But I have here, it's approximately 0.3, so that means 103 watts per meter squared will be reflected, and I'll get 240 passing on through. Now remember, it's going to absorb most of that. The Earth is not a perfect black body, which means it's going to emit some. The average emissivity I've written here is around 0.6, and that means of the amount that lands on it, it's going to re-emit 0.6. Now, normally, all of this would be in balance. The amount of power coming in to the Earth will equal the amount that's going to be sent out to the universe. There are some gases we keep talking about in the news, greenhouse gases, and so why are they so important? Well, these greenhouse gases have a very specific characteristic, and that means that their natural frequency of vibration, so their resonant frequency, is very close to that infrared radiation I was talking about that would be coming from the Earth back out to the universe. Now, that means instead of it going out to the universe, it's actually going to absorb it. And when it gets absorbed, eventually it has to be released, and when that happens, it's going to be released in all directions, not just the direction it was originally coming from, that is, from the Earth. Now, some of it will leave, but some of it is going to be redirected back to the Earth. And it's going to interrupt that balance I was just talking about. So, not all gases can do this. There are 4 here that I suggest you know about: methane, CH4, water vapor, carbon dioxide, CO2, and nitrous oxides, of which one of them is N2O. There are both natural and human activities that are going to cause these gases to be released into the atmosphere. So let's take a moment and talk about some of those sources. Naturally, water will be in the air, but humans will also increase with irrigation. Now, the fancy name for human activity is anthropomorphic, but that's a big mouthful. I also would suggest that my gender had something to do with this as well, so don't let me off the hook by saying it's man-made. Humans are all part of the problem. Carbon dioxide, yes, naturally we get it from forest fires and volcanoes, but we also get it from burning fossil fuels and deforestation, because normally plants would be taking the carbon dioxide out of the air and putting it into other forms. Without all those trees, more carbon dioxide will stay in the air. Methane is also sometimes called marsh gas. It's also in the permafrost and frozen inside. It's when bacteria is breaking down plants and animals in anaerobic or without oxygen, and then they end up making methane for those plants instead of carbon dioxide like when we breathe. Human activity, we're increasing the number of farm animals, and we're also creating more with natural gas. Nitrogen oxides, yes, we get some from the soil and oceans, but in our engines, our combustion engines, with those high temperature and pressure, nitrogen, which is normally inert in our air, will actually combine with the oxygen and make this. This is what's going to be the basis of a lot of the pollution we see in cities from our cars. I do want to add one more piece in here. It's not specifically mentioned in our syllabus, but it does come up in a lot of questions. And that's the idea of positive feedback. Now, if you're a biologist, you understand this, and we do a lot of these inside the human body, positive and negative feedback. In terms of the greenhouse effect, we want to be thinking about what happens as the Earth warms up. Well, if we have more ice melting, that's going to affect that albedo, which again is going to affect the power balance. We also will start to affect the ocean waters because it affects the amount that's going to evaporate. And remember, water vapor is a greenhouse gas as well. But as the Earth warms, we get less being scattered and more will be absorbed by the Earth, causing more ice to melt. Or here, we have more water evaporating into the air, which is a greenhouse gas. Again, it will absorb more in the air and then re-radiate more back to the Earth, causing the temperature of the Earth to warm some more. We call this a positive feedback loop because when the variable increases, it causes more of the change. An example of a negative feedback loop would be, I'm really hot, so my body starts to sweat, but the sweat will actually reduce my body temperature. That would be a negative feedback loop. Now, we do say enhanced greenhouse effect because without our atmosphere, our world would be much colder than it is. So we already did have a balance. What we're talking about is how much we have changed it. Now, let's just go through first and say, well, what would happen if the greenhouse gas didn't re-radiate this energy back to the Earth? What temperature would we have here on the Earth? I've got here, we got a solar constant. That's in our data booklet. And I'm going to use the average albedo value of 0.3 and average emissivity of 0.9. So let's think about what we're going to have in terms of an intensity to the Earth. Now, first of all, this is the intensity that arrives at the Earth, but that's going to be arriving as a circle. And then it has to be projected onto the sphere of the Earth. So of this, only 340, or this value divided by 4, will actually reach the surface. Of that 340, because there's an average albedo of 0.3, that means the intensity getting to the Earth is going to be around 238 watts per meter squared. Now remember, we need to have this idea of an equilibrium. So if that is the amount that's landing on the Earth, we need to then think about how much power the Earth is going to be releasing. Anything that has a temperature will emit radiation. So I'm going to use Stefan-Boltzmann's law here, and I'm going to use the value for a non-black body. Power is emissivity times Stefan-Boltzmann constant times area times the temperature to the power 4. I'm going to move the area over to this side because power over area is my intensity right here. And this is going to be 0.9. 5.67 times 10 to the minus 8, my favorite constant, times the temperature to the power 4. And remember, this is 238. If I rearrange that and put in my value, I'm going to get 261 Kelvin. And that's going to be negative 11 degrees Celsius. That would be our surface temperature if we didn't have an average. Now we know that the average temperature of the Earth is not minus 11. Yes, some places are colder and some places are hotter, but it is greater than this. Why? And that's because we have an atmosphere that naturally would absorb some of this and return it back. Now remember, we have also from Wien's law, lambda temperature is 2.9 times 10 to the minus 3. And if I do this, and I put in my value of 206 Kelvin, I get a wavelength of 1.1 times 10 to the minus 5 meters. This is in the infrared radiation range. You can check that out in your data booklet. Now, that is the range that we're talking about that can be absorbed by the greenhouse gases. Not just any gas, but the greenhouse gases will be able to can absorb in this range. That means they would be absorbed and then eventually released and released in all directions, including back to the Earth. That would imply that I would have more power incident on the Earth, and that would, through our calculations, give a greater temperature of the Earth. It is this energy balance that it's going to be very important that you can apply to some of your questions. Well, please read the success criteria that I hope you can say yes to all of these points.